In this video, I'm going to show you how in MATLAB to use the provided function tlcalc to calculate transmission line parameters such as characteristic impedance, distributed inductance, distributed capacitance, and also visualize fields around the line. Let's go ahead and get started. So the first thing I'll do is create a new script file. And the first line, I like to start off with the name of this. Let's call this demo tlcalc, and it will be .m. So what I'll do is I will copy this. I will say save as. I will paste the name and say save. Okay. So let's remind us that this is for EM possible. And the very first functional thing I like to do in my code is initialize MATLAB. And I do three things. I close all open figure windows. I clear the command window, and absolutely most important is to clear all of your memory. The next thing I like to do is define units. So we will put this in terms of MKS. So we will set meters to 1 and seconds to 1, and we're not going to deal with mass, so we don't have to worry about that. Given those, we can now define other units, such as millimeters. And that's 1 times 10 to the minus 3 times meters. I'll stick with just millimeters, but we could define micrometers, nanometers, whatever else we wanted. So to measure frequency, we need hertz. That is 1 over seconds. And then kilohertz is 1 times 10 to the 3 hertz. And I will copy and paste that twice, and I'll give myself a megahertz and a gigahertz. So megahertz is times 10 to the minus 6, and gigahertz is times 10 to the 9. I think I said minus 6, I meant to say positive 6 there. And because I'm strange, I will line up my equal signs. I think it looks nice, and nice looking code runs better, absolutely. Just to make sure we haven't made any mistakes, I'm going to click the Run button up here. That saves and runs it. And just make sure it doesn't error out, in which case it's easier for me to correct any mistakes that we might have made. Given these units, we're ready to enter our constants. So our free space permittivity, free space permeability, and speed of light. Let's start off with the free space permeability, U0. I like to type in all possible digits that I can possibly bear entering, and I have no illusions that my model is actually accurate out to all those digits. I think that's just good practice for computation. So we will enter 1.25663700614 times 10 to the minus 6. Free space permittivity, 8.85418788176 times 10 to the minus 12. Whoops, that should be a semicolon. And then speed of light, 299792458. And if I really wanted to be strange about this, I might say times meters per seconds, but I kind of know I'm already doing MKS. I wouldn't really need to do that. I haven't defined henries or farads, but I could say times 1 over meters for my units. I tend not to do that, but it's probably better practice to do it. Okay, so that's it for initializing MATLAB and initializing the program. Now we're ready to get started and do things related to our transmission line. So we will create a section header. We'll call this very first section the dashboard. Inside the dashboard is all of the hard-coded numbers defining or saying anything about what I want this program to do. So this is where I include dimensions of the transmission line, material properties, frequency where I want to operate, anything to control the numerics of the algorithm. But I don't do any work in the dashboard, just the hard-coded numbers. And you'll know you've done something wrong if you finish your simulation, and then maybe I ask, okay, but now simulate it with this dimension being twice what it was. If you have to change anything other than that one number in your dashboard, then you're doing something wrong in your code. So this is very good practice to write your codes this way. So the first thing on the dashboard, I might want to define the frequency where I want to operate the transmission line. Call this F naught, and let's put this at 2.4 gigahertz. The next are transmission line parameters. These are not things like characteristic impedance, distributed inductance. Those are what we're going to calculate from this whole simulation. These are dimensions and material properties. So the dielectric constant of the substrate, let's set that to 6.0. The thickness of the substrate, let's set that to 2 millimeters. The width of the transmission line, let's set that to 3 millimeters. And again, we'll line up the equal signs. And last, the grid parameters. So I always like in my codes to define an NRES parameter. This will be the number of points that we resolve something with. And so in the case of our microstrip, I'm going to choose it to be the width of the microstrip. So we're going to use 10 points on our grid to resolve 3 millimeters. And it gives us a way just to control the resolution. The physical width of the grid, at this point, we just sort of have to make a guess. Let's just go with 15 millimeters for right now. We know we need a spacer region around the line, and we'll enter 15 for now. For SY, we'll go with 10 millimeters. And I will line up my equal signs. We're done the dashboard at this point, and if we forgot anything, we would just go back and add it. But let's go ahead and run this just to make sure we don't get any errors, make sure we made no typos. So all looks good so far, and we're ready to go on to the next section. So in the next section, I will copy and paste my section header, and we will call this Calculate Optimized Grid. We're going to do some funky stuff here, and we're doing this to make our simulation more accurate and get away with fewer points on the grid. So the very first step, I'm going to calculate the initial grid resolution. So that already implies we're going to adjust that in some way, and we absolutely are. So dx, as promised, we're going to resolve the width of the transmission line by NRES number of points. And for now, we'll just set dy equal to the same thing. Next step, we will call this snap grid to critical dimensions. So we already know that we're going to resolve the width of the transmission line with exactly 10 cells. But you know what? Maybe we start off by some other dimension, and that's not necessarily a fractional number or an integer number. And so maybe we're resolving W by 10.5 grid cells, in which case we can't fill in a half grid cell. We're going to be off. So we're going to adjust our grid resolution so that we resolve W and in the vertical direction H with an exact integer number of grid cells. So the first thing I'll do is I will calculate how many grid cells wide W is. So W over dx. Now this might come out to be 10.5, 11.7, something like that. And we need this to be an integer. So we're going to round that. And I like to round up so that we do not lose grid resolution. We don't want to go wider grid cells. If anything, we want to make our grid cells smaller to increase the resolution so we're not losing accuracy. So that's why I round up. So at this point, we know that we want to resolve W with this many cells, but if we do that right now, that won't be correct. So in order to make that correct, we have to recalculate dx as W over little nx. Now we've adjusted dx, we've made it a little bit smaller so that W is resolved exactly with little nx number of cells. I'll copy and paste this and do the exact same thing for the y direction. I'll just change all the x's to y's. And our critical dimension now is not W, it's H. Let's go ahead and run this. Okay, and no errors. So the next step now is to calculate the grid size. We know its physical size, that's Sx by Sy, but how many total number of points do we need? So that's the next step. Total number of points horizontally is Sx over dx. Now there's potentially a problem here. We didn't consider Sx at all when we calculated dx. This could come out being also a fractional number like 100.7 or 112.3, something like that. So what we'll do is round up again. Now we don't want to, our grid's now off. Sx and nx are not compatible. They're off by a little bit. And I don't want to recalculate dx because I already set dx to make w resolved exactly. So what I will do is recalculate Sx as nx times dx. And in my code, I don't actually use Sx again, but I don't want my parameters to be inconsistent moving forward. So we'll copy and paste this, and we'll do the same thing for the y direction. We'll go ahead and run it. And at this point, it's good to actually check the values of nx and ny. And what I'm looking for is to make sure that those numbers aren't anything like, a million or something completely ridiculous. So 50 and 24 seems small, but reasonable at this point. So we'll go with those numbers. For graphics purposes, we'd like to create some axes so that we can plot our device and label x and y axes correctly. So that's our next step. We'll calculate these, what I call the grid axis vectors. So we'll have a one-dimensional array along the x-axis that calculates the position of each point along the x-axis, and then the same thing for the y-axis. So we'll call the x-axis xa. We'll create an array that goes from 1 to nx times dx. And what I would like to do is center my grid around 0. So I'll just say xa equals xa minus mean xa, or the average value of xa. That centers it around 0. And we can do the same thing for the y-axis. So I'll go ahead and copy and paste. Sometimes I won't center the y-axis. Other times I do. Maybe it just depends what mood I'm in more than anything else. And remember, this centering and these axes, these are just for the graphics at the end for displaying your device. Nothing numerically here will have an effect later. I'll run this just to make sure I don't get any errors. Okay. Now at this point, we're going to the next section of our code. This is where we're going to build our inputs. So we'll say define inputs. We're after 3 different two-dimensional arrays. One that describes the dielectric function, and then the other 2 describe the location of the conductors for each of the 2 conductors. So let's start off with conductor 1. Conductor 1, this is the conductor of the actual microstrip. So we need to calculate what I would call start and stop indices. So indices along the x direction, indices along the y direction of where we're locating this. So to do that, let's first calculate how many cells wide the microstrip is. And if I've done my work, I know that it's NRES and all that above, but I like to write my code so it doesn't necessarily depend on what comes before it. So I'm going to recalculate that. W over dx. And notice I'm rounding here. I'm not rounding up or down. That's so I get the closest possible representation, just in case I'm doing something above so that W is not my critical dimension. I've done something else for some reason, and I'm going to get as close as I can to that, the actual physical width of the line, representing that on the grid. My start index. What I would like to do, figure out where the start and stop indices of these. So the start index, the middle of the grid is big nx over 2. And I want to back up by little nx over 2. And that will bring me to my first grid index. Well, I'm going to factor out the 1/2, the divide by 2. So in parentheses, I'll have big nx minus little nx. And it's all divided by 2. And this nx1 needs to be an integer. Well, since I'm dividing by 2, that may not necessarily be an integer. So I'm going to have to round that. Now I have my start index, which makes my stop index pretty easy to calculate. It's my start index plus the number of cells wide minus 1. I have to subtract 1 so that I'm not off by 1. So for example, if little nx was 2, I needed to fill in 2 grid cells. If nx1 was, let's say, 10, and I didn't subtract 1, I would get 12 for nx2. I would end up filling in 10, 11, and 12. I would have filled in 3 cells. So I subtract 1 so that I'm not off by 1. And little things like this can make a big difference. We need an NY. We need the vertical position of the microstrip. So we want to go to the bottom of the grid. We want to subtract how many cells tall our substrate thickness is. So that's h over dy minus 1. Now we have the minus 1 because we have the ground at the bottom that will be overwriting one of those cells. So we actually need to make this, we need to come up one more cell than we would have thought of if we didn't think about the ground plane overwriting one layer of our substrate. Okay, now we're ready to actually build conductor 1. We'll call that C1. The first thing I'll do is just initialize it all to zeros. And then we'll go ahead and place in the microstrip. That's going to go from NX1 all the way up to NX2 at a position of NY in the vertical direction. And we'll set those to 1s. All right. Let's show that. So show arrays. Eventually, I want to show 3 arrays. So I'm going to use the subplot command. And I want 2 subplots tall, 3 subplots wide, and for conductor 1, I'm going to put this in the second subplot. And we don't have to put commas there, although we can. I'll put commas in, but they don't have to be there as long as these are all single digits. MATLAB lets you do that. So let's go ahead and draw this. So we'll say image SC, XA, YA, C1. We're going to transpose that because MATLAB thinks arrays are matrices, and we're thinking in terms of X and then Y. But with matrices, this first number would actually be vertical position, the second number is horizontal. And the way to fix all that is to keep everything X comma Y, but just transpose something when we're about to image it to the screen. We'll go ahead and run this and just see where we are. Make sure we don't have any errors. Okay. So we have something that does look like 2 subplots wide. Looks like it's going to be 3 wide and 2 tall. And so there's our microstrip. Let's do something else. Let's say axis equal tight. This is something you almost always want to do to show the device proportioned correctly. If we didn't do that, the microstrip might look too thin or too tall or anything else. I'd also like to see values. I mean, should we just assume that blue is 0 and yellow is 1? I don't like to do that. So I'm going to give this a color bar. I'm also going to title it. And we'll call this C1. We'll go ahead and run it. And that looks pretty good. Now we see that yellow is 1 and blues are zeros, and that looks correct. All right, back in. Conductor 2 is the next thing. C2, we'll initialize it to all zeros. And then go ahead and add the ground. That's going all the way across, and it's all the way at the bottom of the grid. Just to make sure we're doing this correctly, we also want to image our second conductor. So I'll copy and paste the code from the first. We will go to the third subplot. And now we're imaging C2. We'll also title it with C2. And we can see we have our yellow line running across the bottom. That's our ground plane. Very last input is our permittivity. So this will initialize all to 1s. We don't want zeros in the permittivity because permittivity is always greater than or equal to 1. So by putting all 1s everywhere, we've just put air everywhere. But we want to go ahead and add the dielectric. The dielectric goes all the way across, and it goes from NY, that's the position where the microstrip is placed, all the way to the bottom. And we're going to stick in values of ER. That's what we defined up in our dashboard as the dielectric constant of the substrate. And just to make sure that we're right, Let's go ahead and copy and paste our imaging code. In this case, we're going to the first subplot. We're showing ER, and we will title it with ER. Now we can go ahead and run that. And what we're looking for here is an alignment between the microstrip and the top of the substrate. You know, for some reason our microstrip was way up here or something, then and floating above our substrate, that wouldn't be correct. So everything looks roughly correct. Another kind of neat thing that we can do, we can just create an A. We'll just add all these together. ER plus C1 plus C2. We clear the command window and just do an image SC XA YA A dot transpose. And we can look at everything added up and see where everything is. And again, our microstrip's not floating up here. Sometimes I'll put it above, sometimes I'll put it in here. And believe it or not, this works actually a lot of times just as good or better than putting it above. And that's, we're getting too much into the numerics, but underneath the hood, there's a staggered grid going on. And if we put our microstrip at one cell above the substrate, it's farther off of the substrate than it actually is. It's 2 half grid cells up here. It's only 1 half grid cell down. So it ends up being a slightly more accurate way to do this. That aside, as long as you're checking for convergence, you would never have to know something like that, and everything would work just fine. That's a subtle little thing. Okay, so everything looks like it's working correctly up to this point. Now we're actually going to simulate the transmission line. All of our inputs are ready, and that's what we do next. Simulate transmission line. So the very first thing is to call the tlcalc function. So the outputs, let's get all the outputs. So we want the characteristic impedance, we want the effective index, we want the distributed inductance, we want the distributed capacitance, we'd like to see the electric potential, we want the X component of the electric field, we want the Y component of the electric field. And we're calling tlcalc. And then the inputs we give it, we're giving it the dielectric function, we're giving it our 2 conductors, we're giving it the grid resolution, and we're also saying what kind of transmission line this is. It's a single-ended line or an unbalanced line, so we give it a 1. All right. Let's run this just to make sure it all runs and doesn't error out. Okay, it has run, and it left this little message here to showed you that it ran. And we can type in, we can look, what was the characteristic impedance of that line? 59 ohms. N, L, C, and a V and EX and EY we can't really do at the command prompt, but we can image them, which is exactly what we'll do. I'll go up here, and I'll copy and paste all of this imaging code, so we don't have to retype that. I'll paste it below. And now we want to go to subplot 4. We'd like to see our electric potential. We'll also label it electric potential. We'll go to the 5th subplot. This is where we'll look at EX. We'll also label it with EX. And then the very last one, the 6th subplot, EY and EY. And if these look like noise or something crazy, we know that something went wrong with our simulation. They should look like nice, smooth functions. And that's what we're seeing here. We can't say yet that we're getting accurate answers, but we can say we're getting at least a correct answer for the information that we gave at the grid resolution and all that. All right, maybe we want to display results. And so this is where we're going to display to the command prompt the impedance of the line and that sort of stuff. So disp, and we'll go in square brackets here. Let's say Z0 for characteristic impedance. Number to string. Z0. And that has units of ohms. And I want a space between the number and the, let's go ahead and run that just to make sure that that displays correctly. And that displayed correctly. Now we can copy and paste that. Let's go ahead and display our beta. Let's calculate a beta. We haven't calculated that, so if we tried calculating, that would error out. But our units will be radians per meter. So let's go ahead and calculate beta. Calculate constant or phase constant or beta or whatever you'd like to say. So our wavelength is the speed of light over the frequency, which makes our k naught, our free space wave number, 2 times pi over wavelength, which makes our beta k naught, times the effective index that was calculated by our simulation. And I'll line up the equal signs. Now that we run it, we should get a beta that makes some kind of sense. 106 rads per meter. That makes sense. All right. Next, maybe we want to display the effective refractive index. And again, I like to line up my equal signs even for my output. So we'll put an N here. And there are no units for a refractive index, so we will delete that. Let's just keep going before we run it again. We probably want our distributed inductance. So we'll say L. And so this comes out being henries per meter. And C, display C, and that is farads per meter. Let's go ahead and run it. Close this figure window just to get that out of the way. And we have all very reasonable numbers here. Okay. Very last thing we need to do is convergence. The best way to do this is to generate a plot of something like impedance versus grid resolution. We're going to do this a little bit more crude to be more succinct. And so first thing is we might want to look at the spacer region. So let's start with just 5 millimeters wide. And we'll run this. And what I'm looking at is the impedance. I'm seeing 44 ohms. So I'm going to double it. And run it. We went from 44 to 57 ohms. That's a pretty big jump, so I want to keep going. Let's keep going in increments of 5. Right now we're at 57.6 ohms. 59. Do we consider that a big jump? Maybe, maybe not, depending how accurate you need to be. Let's go ahead and jump another 5. So it went from 57 to 59, and let's see where we are now. It's staying at about 59. So we could stick with 15 or 20 because both of them gave us 59. Let's stick with 15, the smaller number. And we could do the same thing with the vertical spacer. Let's start with 5. See what number we get. We get 51 ohms. Let's double that to 10. And we get 59 ohms, so we went from 51 to 59. That's a big jump. Let's go up to 15 millimeters. So right now we're at 59.5 and 60.1. Is that significant? Maybe, maybe not. Let's just try 20. And that hardly changed at all, so I would probably back off to the smaller number, to 15. That was just for the spacer regions. We also want to look at the grid resolution. So let's start at 4 and rerun it. So with a NRES of 4, in other words, we're resolving our microstrip line with 4 cells, we get an impedance of 70 ohms. Well, let's make that 10. We went from 70 to 60. That's a pretty big jump. Probably want to keep going. Let's go up to 15. Now we're down to 56. From 60 to 56. Is that significant? Maybe. Let's go to an NRES of 20. We're at 56.9 right now. 53. Let's try 25. 52, I don't think that's converging, but you get the pattern. And probably what I'd want to do is once NRES converges, go check my spacer regions again, just go back and forth a few times. And manually, this is a bit cumbersome. Really, the better way to do it is to create a plot of impedance versus NRes for maybe NRes from 2 up to 50 and see how it behaves. So that's it. That is how you simulate a microstrip transmission line using TLCalc.